Alright, the last review topic we are about to discuss is a linearization. After you derive your equations of motion, the final results will be all summarized into a form x dot equals to a vectorized function fxu. Where x and u are state variable and control variables, which are also vector quantities we will define after a while. Now we want it to be linearized x dot prime equals to ax prime plus bu prime shape, where a is an n by n and b is an n by m matrices. The prime symbol is nothing but a deviation from a reference point, just like what you have done in the perturbation theory. For example, x prime is x minus xe and u prime is u minus ue, where xe and ue are constants describing states and control inputs for the hovering conditions or any other flight conditions. Of course, you know that this rate of change is needed for you to understand the dynamics itself or building your own flight simulator, because you can propagate to the next state by simply integrate dx at time step t with the relationship for the simplest discrete case. Your state and control input at time t will give you the rate of change of your state, which propagates your state to the next time step t plus 1. Given your control input at the next time step, this procedure will indefinitely continue. Then why do we simplify our dynamics with this linearized equation? Obviously, one reason is that it is computationally simple. Similarly, in designing optimal controllers, such as LQR, LQG, or H infinity, requires linearized equations to get their solutions. If you have enough computational power and about to design a nonlinear controller, you can skip this part, in fact. Alright, let's get to the point. Linearization using Taylor series expansion can be done like this. Any function f, in our case x dot, can be expanded up to the first derivatives, such as f xe ue plus partial f partial x at x equals xe u equals ue times x minus xe plus partial f partial u at x equals xe u equals ue times u minus ue plus higher order terms. Since the reference state and control inputs are all constant, and by the definition, of x prime and u prime we can summarize this Taylor series expansion as x prime dot equals ax prime plus bu prime shape, where A is a Jacobian matrix for this partial f, partial x, and this B matrix stands for partial f, partial u. For example, your A matrix would be look like this. Now, I guess we are ready for starting the dynamic modeling of a Quadrotor UAV.